the photodiodes are part of an optical receiver, and the performance of the receiver is an important part of the optical communication system because it requires operation at very low power levels. I mean, if you have a transmission system where the light is propagating over long distances, and even if the attenuation in the fiber is very low, after, for example, 100 kilometers with 0.2 dB per kilometer, after 100 kilometers, the attenuation is 20 dB. And so if you have 0 dBm input power at the receiver, you may have minus 20 or even lower optical power. And so the receiver has to operate at very low powers. At the receiver side, noise is generated that is added to the signal, which defines a certain signal-to-noise ratio. And depending on the signal-to-noise ratio and the required signal-to-noise ratio, we may have different operations of the receiver. And so that's what we are going to see now. As always in this course, we are considering digital transmission systems, and specifically intensity modulation and direct detection optical receivers, where we assume that we are transmitting bits of information. And at the receiver, we use direct detection, where the photodiode is used to convert the optical signal directly to an electrical signal. And this type of optical receivers are known as direct detection because they convert directly optical power to current. And then we have a common way to describe or analyze the performance of the receiver is in terms of the eye diagram. That's what we're going to see now. And then finally, we need to analyze the full receiver performance, which is defined in terms of the signal-to-noise ratio at the receiver. And for that, we need to assess the types of sources of noise at the receiver and the signal-to-noise ratio. That's what we're going to see now. Noise plays a fundamental role in the design of an optical receiver, as you see here. So we have electrical pulses that reach the transmitter. The transmitter is made of, as an optical source, a light-emitting diode or a laser transmitter, which converts the electrical signals to optical pulses, which are transmitted through the fiber. The fiber attenuates and distorts the pulses, where the pulses become wider. And then they are detected at the receiver by means of a PIN photodiode or avalanche photodiode, which converts those optical pulses in electrical current pulses, which contain also noise added by the receiver and the photodetector. And then we have followed by an amplifier and possibly some filtering to reduce the noise. And then at the output, we have some voltage pulses. Once we have these pulses, I'm sure you understand that we need to have some means at the receiver to convert these pulses to digital information. And so to make a decision at the receiver whether a bit 1 or a bit 0 has been transmitted, right? And so we need some kind of decision circuit that decides which type of bit has been received, and possibly followed by some additional signal processing. So here we have a diagram of direct detection for on-off keying signals. So we have the photodiode, which has a certain voltage to reverse the bias the photodiode, followed by, and so at the output of photodiode, we have some a certain current associated with the input pulses, optical pulses, which are then pre-amplified, possibly some additional amplification with some automatic gain control, some filtering, and then our decision circuit. The decision circuit requires information about the data rate of the signal being transmitted. And this data rate information is provided by what's called the clock signal, that will sample the received signal to decide whether a 1 or a 0 has been transmitted, and some circuitry, which is usually known as the clock recovery circuit, is required to recover the clock information from the data being transmitted. And then the decision circuit compares the input voltage with a threshold voltage at the time of decision, and decides whether a 1 or a 0 has been received, depending on whether the received signal is below this threshold voltage or above the threshold voltage. Just have one slide here just to mention that if NRZ codification is sent at the transmitter, the NRZ data does not have clock recover and is more difficult to obtain clock information from the data. And there is the need to convert the NRZ to a type of RZ type of waveform to recover the clock information. And this is just a slide just to show, I mean, I'm not going into much detail, but this is a simple circuit that from the NRZ information, which involves delaying the data by half of clock and then multiplying it, gives rise to a clock component, which can then be filtered and obtain the desired data rate or clock information. Okay, but I'm not going to much detail. Basically, the decision circuit is a comparator, where in one of the inputs you have the certain threshold voltage that you can adjust, and then the other input you have the data being received. And so the output of this comparator is 0 voltage or a high voltage, depending where the signal is above or below the threshold voltage. For example, suppose you have something like this. Suppose this is the threshold voltage, and we have the signal, and we have the signal coming through, which has noise, and sometimes goes below, is 0, goes above. And so at the output of the comparator, we have something like this, just voltage. But if the signal is very low, and if the signal has variations close to the threshold voltage, then what happens is that you can have a continuous change in the signal at the output. And then which may become a problem when we have noise and the signal is very low. But basically, the clock information is used to sample the signal at a certain instance of time. For example, ideally, it should be at half the bit period, if this is the bit period, okay, which samples the signal at these points, okay, at the output of the decision comparator. And so this is a simple way of recovering the data information being sent as bits of zeros and ones. And so at the output of this flip-flop circuit, you have the recovered data. So that's just, this slide is just an explanation of what I've just discussed. And so one way to assess the performance of the receiver is to do a plot where you superimpose several bits of information, zeros and ones, in the same time window. And the aperture of this diagram, which is called an eye diagram because it looks like an eye, the aperture of the eye diagram gives you information of the quality of the signal being transmitted. So any questions so far? Okay. But since noise is added at the receiver to the signal, this may give origin to errors in the decision circuit. And the performance of the receiver can be measured in terms of the bit error rate, which is defined as the number of errors being received over the total number of bits being transmitted. So this equation here, okay? So this the number of errors over the total number of bits being transmitted. And the total number of bits being transmitted is the bit error rate times the total time that the measurement has been done. And there's an important definition, which is this one here, which is the receiver sensitivity, which is defined as the average power required at the receiver to obtain a specific bit error rate. Okay, so if the average power increases, then this is equivalent of increasing the signal to noise ratio. And so the number of the bit error rate should be smaller. But if the average power at the receiver decreases, which means the signal power is smaller, then the signal to noise ratio, assuming the noise is constant, the signal to noise ratio decreases. And so this parameter, which is the average minimum power at the receiver to obtain the specific bit error rate, is an important parameter. The signal to noise ratio definition is given here, is defined as the signal power from the photocurrent at the output of the photodetector divided by the total photodetector noise power plus additional electrical noise added by the receiver. And so now the question is, what are the sources of noise at the receiver? And this slide gives you a summary of all the sources of noise present at the optical receiver. First, as you see here, in the we have a stream of photons being transmitted, which hit the photodetector. For a specific optical power, so if we assume we have a specific optical power, and even for a constant optical power, the number of photons hitting the photodiode is actually statistically dependent and follows a Poisson statistics or Poisson fluctuation, which means there's an average optical power incident at the photodetector, but the actual number of photons hitting the detector actually changes over time, although the average power is constant. And this obviously generates some noise at the detector, which is known as the quantum noise. All right. Then at the photodetector, there are several types of noises that can exist generated by the photodiode. And the first one that is shown here is the bulk dark current. Bulk dark current means that even when there is no light incident in the photodetector, through thermal vibrations of the atoms, there might be, some of them might acquire enough energy so that an electron and hole is generated within the photodiode, giving rise to a current. And so even without incident power, that might be a small current flowing in the device, which is taken as some kind of noise that is generated in the detector. And this is known as the bulk dark current. And dark current because even when there is no light or dark, there is some current flowing in the device. There might be some additional surface leakage current, which is also dark current, but that doesn't cross the p-n junction, which is also some type of noise. And in avalanche photodiodes, we also have avalanche gain. And this avalanche gain is also statistical in nature. And so there's some gain fluctuation, which gives rise to additional noise as well. And then in the electrical part of the circuit, we have thermal noise generated by the resistances and amplifier noise generated in active devices. And so all these noises are combined to define a certain signal to noise ratio at the receiver. Okay. As you probably know, thermal noise and amplifier noise, they follow closely a Gaussian distribution, whereas photodetector quantum noise follows a Poisson distribution. And so the combination of these two different statistics is actually very difficult to treat mathematically. And so we're going to do some approximations to be able to do some simple calculations on the probability of error and calculation of the signal to noise ratio. And so starting with quantum noise, as I said, quantum noise follows a Poisson distribution and is a result of the random arrival of photons generation of carriers to the photodetector. If we have a certain power incident in the photodetector over a certain interval of time, tau, to take the average number of carriers generated over this interval of time, we have to integrate or taking the average of the total optical power over this time, multiply by the responsivity, which gives us the current, And if we divide the current by the electronic charge, then we obtain the total average number of electrons generated at the receiver. If we substitute the equation we obtained previously for responsivity, we obtain the following result, where this quantity E corresponds to energy received over a certain interval of time, in this case, interval of time tau. And so if we have a certain average, so a certain average number of carriers received at the photodetector, the actual number of electron-hole pairs over this interval of time varies according to the Poisson distribution, which we know is given by this equation here. And this equation tells us the following. If we have a certain average number of carriers being detected, which is defined by this capital N bar, the probability that the number of carriers generated is small n, so this will be the actual number of carriers detected. So the probability that the number of electron hole pairs is small n, given a certain average of carriers being generated at the detector, is given by this expression here. Okay. For example, let's see an example. Suppose we have an optical communication system that is operating at 850 nanometers. The beta rate is 10 to the minus 9. And we want to find out what is the energy required in the pulse to have a probability, so that the probability is 10 to the minus 9, and that a logical 0 is detected when a 1 is being transmitted. And so here we have to consider the following. If a 0 is being transmitted, okay, sorry, a 1 is being transmitted, and we want to obtain the probability that a logical 0 is detected. And for a logical 0 to be detected, we can assume, for simplicity, that we should have measured no electron carriers in the photodetector, right? Because ideally, when there is no power incident at the detector, we know that a 0 has been transmitted, right? So going forward, so we want to know the probability that when a certain number of a certain power or in a pulse duration is sent, what's the probability that the number of carriers detected is equal to 0? And the probability should be less or equal of 10 to the minus 9. And so we need, so the equation we need to solve is this one. So the probability that the number of carriers detected is equal to 0, even when a 1 has been transmitted. And this should be equal to 10 to the minus 9. is if we solve this equation for, and we know that this equals, as seen here, okay. So we need to solve this equation here, n equal to 0, which gives for n equal to 0, this equation is equals e to the minus n. Okay, and if we solve this equation, so e to the minus n bar equals 10 to the minus 9. If we take the logarithmic of this equation, we have minus n bar equals minus 9 logarithmic of 10. And so changing this number here, the sign, we have this, this result, okay? And so this tells us that to have, if quantum noise is the only source of noise, to have a probability of error of 10 to the minus 9, assuming that when a 1 is being transmitted, we need at least on average 21 electron hole pairs generated within this pulse. Assuming a certain quantum efficiency, and so if we divide this number 21 of electron hole pairs by the quantum efficiency, we have the required number of photons at the detector. And this number of photons, when we multiply this by the energy of each photon, we have the total energy contained in this pulse, okay? Now, if we want to calculate the sensitivity of this receiver, for example, for a bit rate, assuming that the bit rate is 10 megabits per second, which means that the pulse duration, the bit period is 1 over 10, sorry. Yes, I was saying that the bit period is 1 over the bit rate, which is 1 over 10 to the 6, which is 0.1 microseconds. Okay. And so if I have a sequence of pulses, for example, 1, 0, 1, 0. So this will be a 1, a 0, a 1. And this is the duration of the pulse. Okay. And we know the energy contained in this pulse is equal to E. And so the power associated with this pulse is the energy divided by the bit period, which is this term here. Okay. But on average, the average power, if the probability of occurrence of zeros and ones is identical, 50% for each one, on average, the power is 50% of the maximum power, and so we have to divide by a factor of 2 to obtain the average power. which tells us that the receiver sensitivity associated with this quantum noise is, for a probability of 10 to the minus 9, is 21 picowatts or minus 76 dBm. All right. So, any questions so far? And so this is an illustration of how to do these calculations to obtain the probability of error. And the probability of error in this case should be identical to the bit error rate, which 10 to the minus 9 is equivalent of saying that we should have less than one error in 1 million bits being transmitted. So, as I said, the quantum noise, sometimes also called shot noise, when combined with thermal noise that follows a Gaussian distribution, is not easy to treat mathematically. But if the incident photons per symbol is large, the Poisson distribution can be approximated very closely to a Gaussian distribution, which is the case that we are going to consider here, which means this mean square noise current associated with that noise, assuming a Gaussian distribution, and I'm not going to derive this equation, but this is the expression that we are going to use to quantify the noise generated by the receiver by means of shot noise or quantum noise generated by the photodetector, which is twice the times the electronic charge times the average current times the bandwidth. And so this is equivalent of assuming a spectral density of quantum noise which is average power of the noise, and divided by the bandwidth, which is 2 times Q, electronic charge, times the average current, which is a constant value. And so this is equivalent of a type of white noise, because the power spectral density is constant. It does not depend on frequency. Obviously, this is an approximation, but still valid for all practical purposes. The bandwidth that we are discussing here, that appears in this equation, is the bandwidth of the electrical receiver. Usually, the receiver has a low pass response, and the bandwidth will be the bandwidth defined by our receiver. Okay. Just one note here, which is the average photocurrent associated with the signal that appears in this equation here, has 3 components, which is the signal primary photocurrent plus the dark current, which is the other source of noise that I just mentioned before. So, any questions? In terms of thermal noise, we're going to use to quantify the thermal noise power. This we're going to use this expression to quantify the thermal noise, or the power associated with thermal noise, corresponding to a resistance that is used as at the photodetector to bias the receiver. So what you see here is a common configuration for biasing the photodetector. If you remember, the photodetector has to be reversed biased. This can be done with a simple circuitry, which is shown here. And so we have the diode and the bias resistor, which is connected to ground. So this will be the bias resistor and some positive voltage here, which guarantees that the diode is reverse biased. And this resistance here, or this one, which is the same, this resistance here is associated with it some thermal noise, and the thermal noise generated, or which is equivalent of saying that a certain current is generated by the resistance, and this current can be quantified by this expression here. Again, this is equivalent of assuming a certain type of white noise, because the power spectral density is constant over frequency, where T is the temperature in Kelvin, K sub B is the Boltzmann constant, and R sub L is the resistance. And so you see that the lowest noise is achieved by using a high resistance value here. Okay, this leads, so we may assume that in practice we might use a very large resistance to reduce the noise, but we have to remember that equivalent circuit for the photodetector is sorry, just press something. So we have to remember that the equivalent circuit for the photodetector is a current source with a junction capacitance associated with the photodetector, with some series resistance and a parallel resistance corresponding to the bias resistance. And this circuit here is a low-pass filter. Okay. The bandwidth is decreased, and the bandwidth of this filter is 1 over C times the total resistance. And so if the bias resistance is increased, the bandwidth decreases proportionally, which is which is an inconvenience. Okay, because if you want to reduce the noise, thermal noise, by increasing the resistance, then the bandwidth becomes smaller, and so there's a trade-off here between the two. Okay. So in practice, we need to tolerate always some type of thermal noise at the receiver. The expression we've seen, this is specifically valid for a PIN photodiode, so with no avalanche gain. Okay. If we want to include an equivalent expression for the APD, then the expression has to be modified, and we need to multiply it by the gain square of the gain current square of the photodetector, multiplied by this excess noise factor, which is the noise associated with avalanche statistical gain of the APD. And this can be modeled by a simple expression equal to the APD gain times to the power of x, where x is a value between 0 and 1. If the x is 0, that means that there's no avalanche noise added by the photodetector. And if x is equal to 1, then the noise, the APD noise, is maximum. When considering the dark current, we have to distinguish between two cases in this now, which is, for example, we have the PIN structure. In the dark current, the bulk dark current is a current that is generated inside the device, and so is a current that goes through the device. And so this, the bulk dark current is multiplied by the gain of DPD, because it's generated within the junction, which is multiplied by the avalanche gain of the photodetector. But the leakage current, doesn't go through the junction, and so is not multiplied by the gain of the APD. And so when quantifying the noise associated, the total current noise, we have to include the quantum noise and the dark bulk current and the leakage current. And whereas the quantum noise and the dark current, they are both multiplied by the avalanche noise, the leakage current does not come multiplied by this type of noise, and so has a factor of 1. So we need to make this distinction when considering the APD and the dark current, and the contribution of each term to the total noise at the receiver. And so if we have a certain signal power, and the signal power is this optical power of the pulse hitting the photodetector, which gives rise to a current. And the signal to noise ratio is defined as the signal power and a certain current generates a certain signal power, which is the electrical power associated with this current will be the, let's assume this is our signal current at the detector. So if we have electrical power associated with the signal, we have to take the current and square it to obtain the power. For example, in a resistance of 1 ohm, this will be equivalent to a certain electrical power, okay, generated at the receiver. Additionally, if we are using APD, then this primary photocurrent has to be multiplied by the gain of the APD, and so it comes with a factor of the APD gain or current gain squared. And this is the signal power detected at the receiver. If we divide the signal power by the total sources of noises that we have already quantified, namely the quantum noise, the dark current, bulk current, and leakage current, and thermal noise, we have the total signal-to-noise ratio as defined by this equation. Okay, and so this is an important equation that enables one to determine the signal-to-noise ratio if we know exactly what's the contribution of each noise term at the detector. Okay. Just to finish this part, we've seen that in the laser diode, as the basic nature of the light emitted by the laser diode is a result of stimulated emission, but there is always some spontaneous emission, which is equivalent to noise. And we define at the time power spectral density associated with this intensity noise of the laser, which we define as the relative intensity noise, or RIN, which was defined as the power spectral density divided by the mean square power. And assuming that the relative intensity noise is constant, then to obtain the total noises or current noise associated with laser intensity noise, we have to multiply the RIN factor by the total power, signal power, which we've seen is the primary photocurrent square times the gain square times the bandwidth to obtain the total power. And so if we include laser intensity noise in the equation, then the signal to noise ratio is slightly modified, and we have to include another term which corresponds to a laser intensity noise. Okay. And this noise sets a limit to the maximum signal to noise ratio that can be achieved at the photodetector, because if the receiver doesn't add any additional noise, the noise that it generated at the transmitter, it cannot be avoided, and so it defines the maximum value possible for the signal to noise ratio. Sometimes it's common to define some limiting cases. So what we have here is the study of some limiting cases, okay, which are important to study. The first one is when thermal noise is dominant. This is equivalent in this equation of saying that thermal noise, which is this term here, is the dominant source of noise, which is saying that is higher than all the other sources of noise. And so we could neglect all other sources of noise. And then the signal to noise ratio is simply the signal power divided by thermal noise. Okay, and that's the expression we have here. Okay, and we see that for an APD, when the thermal noise is dominant, the APD improves the signal to noise ratio, because as we see in this equation, the signal to noise ratio becomes multiplied by the gain of APD squared. And so there's here clearly an advantage in using a APD photodetector, because it increases the signal-to-noise ratio by the gain that it provides. In the shot noise limit or quantum noise limit, this is coming to this equation and considering only this first term, which defines the quantum noise. And in that case, in the shot limiting case, we have this expression here. And we see that signal-to-noise ratio in this case is reduced by the factor of APD noise. And so, and so in the shot noise limit, the APD in fact reduces the signal-to-noise ratio. And so there is no advantage in using an APD if shot noise or quantum noise is the limiting factor in the photodetector. And so the conclusion is that there's only advantage in using APD if shot noise is not the dominant source of noise at the optical receiver. And so here we have an interesting result, which is the following. So you see, so I'll try to explain doing a plot here. So if we look into this equation here, if we look into the signal-to-noise equation, we see that the quantum noise is defined by 2 times the electronic charge times primary photocurrent times B times m squared FDM. Okay. And so you see that the quantum noise depends on the signal power as well, or the optical power at the receiver. And so if the optical power is very small, then the quantum noise will be small. But as we increase the optical power, the quantum noise also starts to increase proportionally. And so if this is the received optical power, and if we plot this against signal-to-noise ratio, we see that at very low optical powers, so close to a very low optical power, the quantum noise is very small, and probably thermal noise is dominant. And so we see that the signal-to-noise ratio in that case increases with m squared. and increases with received optical power. And so we see that the signal noise starts to increase. But as we increase the signal power, quantum noise starts to increase until it becomes comparable to thermal noise. And after that point, the signal-to-noise ratio becomes limited by the shot noise, and it decreases with further increase of the gain of the PD. And so we see that in that case, the signal-to-noise ratio starts to decrease. Okay. And so, in fact, I should have put, instead of received optical power, I should have put here the gain of APD. And so for very low powers of the APD starts to become significant, which means there's an optimum value for the optical gain, or the APD gain, that provides a maximum signal-to-noise ratio. And so it's possible to obtain this optimum gain by from the signal-to-noise ratio. So we have the expression for the signal-to-noise ratio, the expression that we had before, which depends on the gain of the APD. And so if we take the derivative over the gain of the APD over the signal-to-noise ratio, and we equate this derivative to equal to 0, which is a function of the gain, then the value that we obtain from this equation is the optimum value. So we are actually going to do these calculations in one of the practical classes, but just to let you know that the expression that we get is for the optimum gain of the APD is this one here, which is obtained by taking, as I said, the derivative of the signal-to-noise ratio over the gain of the APD and equating it to 0, which is an important result, which shows that the value of the gain of the APD is, there's actually an optimum value, which gives us the maximum signal-to-noise ratio. If you further increase the gain, there's no further improvement. Actually, the signal-to-noise ratio decreases.